All right, here's the deal. We have known from the very beginning of the semester that something that we were doing was an approximation. Okay, so here's what we did from the very beginning. We have a population, and we want to know something about that population, right? Let's go back to our favorite color on the campus. I know y'all are probably tired of hearing about that particular example, but we have a population, we want to know something about them, okay? But we don't want to do a census. We don't want to sample or to survey the entire population. So instead, we take a sample, right? Okay. So there's a whole process, and we talked about this like maybe week 1 or so. Maybe not week 1, but maybe week 2. Okay, we take a sample. Okay, number 3, we gather raw data from the sample, right? And we've known from the beginning, this isn't the entire population. This is just the subgroup that we are surveying, right, for whatever reason. It's not the whole field of tomatoes, okay? It's just a sample that we picked, and we weighed them and measured them and all that kind of stuff. So we gather raw data from the sample. We find sample statistics, right? Okay, I'll give you an example. Okay, our sample mean is X bar, right? Okay. Now, I didn't make a big deal out of the fact that it was our sample mean whenever we were doing mean, median, mode, and range and all that stuff. But we knew that's not the entire population, right? It's just our sample. So the sample mean is what we've been working with, the X bar, right? So we do our sample statistics, and then if you'll remember, we said the next thing we'll do is using a margin of error. That's what we said at the beginning of the semester, but now we're going to change that. It's the same idea, but we're going to call it the sample error. Using our sample error, we will, oops, didn't change back my color. We will estimate or approximate the population parameter, right? Okay, so we do all this stuff working just from the sample. We're not looking at the entire population. We find the sample mean, we figure out what's the sample median, we figure out the range on the sample and all that stuff. But eventually, we want to estimate our entire population. The whole point is to talk about what's the stinking favorite color at A&M Commerce, right? So eventually, we're going to use this sample statistics that we find, and we're going to try to talk about the population, okay? So this is called making inferences. Oops, can't write today. Inferences. Okay, now an inference is kind of an educated guess, but we're using numbers to help us get there. So it's not just a guess, we're actually using the math to get there. So this is called inference, and in fact, you might see something called inferential statistics. Okay, there's a couple of different kinds of statistics you can do, and what we're talking about this semester has been inferential statistics, because we want to work off of primarily samples. We don't normally want to use the whole population, so we're going to do that, and we're going to find out something about the population parameter by estimating. Now the problem is that this thing right here, there's an error, right? there's got to be an error, because if we don't take the entire population, if we're only looking at a sample, then it's not going to be completely representative, right? Now, we've done our best to make sure that we don't have any obvious mistakes in there, and that we have a good sample picked, that the sample is indeed representative, and we'll do everything we can to make sure that that happens. But eventually, this isn't the population, so there will be a slight error, right? That's that margin of error we talked about from the beginning, but that's okay. What we're going to do is we're going to develop something called, we're going to create our confidence interval, and talk about the population parameter which hopefully exists, if we've done all of our math right, inside a given range. Okay, so we're going to find our sample statistic. We're going to have this error. We're going to add it and subtract it. It's going to be a lot very similar to whenever we were finding outliers before. So we're going to add it and subtract it, and we'll have these kind of like the fence numbers, a top value and a bottom value, and we're going to say that's our confidence interval. And inside of those, you know, if our sample stats here and we've got this max and min values going on, then inside of there somewhere, we're pretty sure, we're not 100% sure because we didn't do a census, okay, but we're pretty sure that our population parameter is in there. And what we want to be able to say is we want to say that this outcome is statistically significant. Statistically significant. Okay. Okay, so what does that mean? How do we know if something is statistically significant? Well, what we're saying when we say it's statistically significant is we're saying that our outcome didn't happen by accident. Okay, whatever just happened was on purpose. Okay, it could only happen by accident in some percentage of cases. Okay. And if it's statistically significant, and it depends on your study that you're doing, normally they'll look at 1% or 5%. Okay, so what they'll say is, oh, it could only happen at the 1% level, or they'll change it into a decimal, 0.01. They use the variable p. Or 0.05. This could only happen at the 0.01 level. It could only happen at the 5%. Well, if it was 5%, it would be the 0.05, and the P kind of stands for that percentage of times that it could happen by accident. Okay, but because it could only happen in this case 1% of the time by accident, then that means what? 99% of the time, it's happening on purpose, right? And it's happening on purpose because of whatever it is we're doing, okay? So, for instance, if we see this significant difference in the tomatoes that we planted, one with fertilizer, one without fertilizer. One field has fertilizer, one field does not have fertilizer. And we see a significant difference in the weights and the measurements and all that, okay? And we do all the math, we figure out our confidence interval, and we can say it's statistically significant at the 0.01 level or at the 1% level if we know that 99% of the situations, the population parameters we have calculated, would have happened only because it has that fertilizer on that field or whatever our treatment was, right? If it was antidepressant meds, if all of these kids feel better after they take our antidepressant meds, and we do our confidence interval and we figure out it's at the 0.01 level or the 1% level, then we're going to say, okay, we are 99% confident, okay, so the other percentage is the confidence level, that the medication that we gave them, the treatment that we gave them, is one of the things that helps them. It's related to them feeling better. Okay, they're correlated, right? Okay, all this stuff that we've used all semester is coming in. On the other hand, if it's at the 0.05 level or the 5% level, then what would we say? 5% of these situations could have happened where the tomatoes are bigger, could have happened by chance. Okay, but that means what? 95% of the chances, or the situations that happened, are not by accident. Okay, so our confidence level, confidence intervals, tell us the percentage of situations where our outcome must be related to whatever the input variable was. Okay, the independent variable, however you want to think about that. Independent. Okay, so it only could have happened, it happened 95% of the time or 99% of the time only because of whatever treatment we gave them, okay? And these percentages are either at the 99% level or the 95% level. Either way, if you're 99% confident of something or if you're 95% confident of something, those are both pretty big confidence levels, right? Okay, so if you're at that level, then we're able to say it's statistically significant. Okay, that's when they draw out the big gun, so to speak, and they say, oh, we have statistical proof that this is important, that fertilizer really helped those tomatoes, or that antidepressant drug really helped those kids, or whatever it was. You know, we are 99% certain that the favorite color on A&M Commerce campus is purple. Okay, well, that gives us a confidence level to talk to other people about, and that's what's going to be important there. Okay? All right. So that's kind of the idea behind confidence levels or confidence intervals. What we're going to do, though, is we want to make sure that we can actually work with these, and we're going to talk a little bit about the sample errors. Okay, so there's a formula. I'm just going to give you the formula. The sample error, also sometimes known as the margin of error. So if you'll remember, in week 1, we talked about, oh, you add this margin of error and you subtract this margin of error, and I said, oh, we'll figure out how to get there later. Okay, well, it's later. Okay, so it's just because we had to have a lot of math before we could get to what the heck is the sample error or the margin of error. And here's the formula, and you'll understand why we needed to do some math first. The error is 2s divided by the square root of n. Okay, that's the formula. Okay, and I'm going to tell you, let me throw this in here. Sometimes you'll see different formulas in different books. Okay, the last book that I taught this out of, they used 1.96. Okay, so if you look this up, say on the web, what's the formula for a sample error, you might get different formulas, but they're all going to be similar to this. And that's really kind of a matter of how much they feel like that's, the sample is affecting how it's related to the population. So, so yeah, this number in particular, I have worked with other numbers before other than that, so just be aware. Okay, so that's our formula. Well, what does that S stand for? Where S stands for standard deviation, right? Yeah. Well, it took us a while to get to standard deviation. We weren't ready to talk about that in week 1, right? So now we come back and we go, oh, okay, we need that for this formula. And then what else? N is the number of data points, which that has been the same thing all the way through the semester, right? That has not changed. So N is the number of data points. E is the margin of error. We'll just say error. That's what ends up happening. They just call it the error at this point. Okay. All right, so that's what's going to happen with that particular formula. And we're going to talk about how we're going to use it. Basically, we want to develop this confidence interval thing. So what we're going to do is say we have a number line. Scooch this up a little bit. I want to keep my formula there, though. Say we have a number line, and we have our sample mean. Let's just say average weight of tomatoes or whatever it was, okay? X bar is right there in the middle. And we want to construct a confidence interval, okay? Then we're going to do what we did at the beginning of the semester. So we already have experience with this. We're going to add X bar plus the E, okay? So that this gap in between here is however big my error is. Okay, and that error tells me how far off I think the sample is from the population. Now, we did something similar to this when we did the normal curve, right, with the standard deviations and finding outliers and stuff like that. So basically what we're saying here is that the ones that we expect to happen are going to fall in here, right? So we expect if this is my sample mean, we would expect the population parameter to be fairly close to the sample, right? If I chose my sample properly, okay? If I've done all my math properly. So I hope that my population parameter is somewhere in here. Or I added the error, what? It might be below, right? It might be above the sample mean, but it also might be below the sample mean. And again, we would subtract the error, right? We're kind of used to doing that. So again, this distance in here between the sample mean and this minimum here is a distance of E, however big my error is. The distance between here and my maximum here on the range is a distance of E, okay? And hopefully my population parameter is somewhere inside of this distance. So this total distance is called my confidence interval. Confidence intervals are created by finding X bar plus the E and X bar minus the E, and developing the range of values, the interval, that's where that word interval comes in, where we expect the population parameter to fall. I'll say exist. We expect that population parameter to exist inside of that interval, inside of that range. So basically we just add and subtract the margin and, the margin of error or the error, and we find it, okay? So here's the deal. We need a letter to represent our population mean, right? If X bar is the sample mean, then we need a letter, a variable, whatever, to represent the population mean. So we're going to say let, and here's where Greek letters come in, and Sorry about this. I'm not responsible for this. It's the letter mu. Let mu represent the population mean. Okay, so what we're saying is that the population mean is somewhere in this interval, we hope, okay, if we've done all of our math right, and we're going to represent that with the letter mu. Okay, it's a Greek letter. Okay, so here's what happens. We want to know how well it's representing, right? And we want to make sure that we found our samples right. We want to make sure, and a lot of times, I'm just going to say this, like if I did this experiment using my tomatoes and fertilizer, and I found, hey, I think that this is helping. Remember we talked earlier in the semester about you don't just rush out and publish, right? You want to replicate this and do it over and over again. So maybe we'll take different samples and we'll look at different, we'll work this out using different groups. And maybe I'll have some university in Florida do the same experiment, and maybe I'll have some university in Illinois do the same experiment. So we want to make sure we've replicated it and we can do a lot of samples and that it works over and over and over again. So I'm going to show you a picture, and it's just so that you can kind of get a feel for what's going on. If I do that, if I replicate my experiment over and over and over again, okay, this picture, and it's way better than the one I could draw, this picture represents what it might look like. So they're saying that the dots, the big black dots, are sample mean, and that the kind of whiskery things here are their sample confidence intervals. So in other words, for this sample, we have a mean down here, and here's my confidence interval. For this sample, my mean's up here. They're not the same, right? We took different samples. So the confidence interval's here. Here's this sample, there's its confidence interval, and so on. Okay? So basically what we would do is we would do this over and over and over again. They've gotten, I don't know, it looks like 20. Yeah, 20 samples in here with 20 means and 20 confidence intervals. So they do it over and over and over again. Okay, and then we say, well, they say that they are 95% sure that they have the mu. Here's my population mean. They have mu inside of these sample confidence intervals. So what does that mean? 19 out of 20 of these, this mu, the actual population mean. Now, how would I find the actual population mean other than estimating it? I would have to do a census, right? So, but they're saying if we knew that mu was right here, and then we compare it to all of these confidence intervals, we say, oh, yep, mu's in there. Here it's a little above the sample mean. Mu's in there. Here it's a little below the sample mean. Mu's in here. In this case, it's way down here at the bottom of my confidence interval, but it's still inside of there, right? And here and here. Here it's way at the top. Oh, look at this guy. This is the one where I've got my sample mean and my sample confidence interval, but mu does not fall in there, okay? So that's the one situation that makes it 95% instead of 100%, okay? Here, mu falls inside the confidence interval. Here, my mu is really close to this particular sample mean, right? So this would have been a really good representative group here if the sample mean is that close to my mu, okay? But these others, even though they're up or down or whatever, they're not bad because using my error, I'm able to create a confidence interval and mu's still in there 19 out of 20 times, okay? So that's what they want to see, and that's why they want to be able to say, oh, okay, we're 95% sure, or we're sometimes 99% sure that my mu falls inside of where I want it to fall. Okay, that's the idea. Okay, if you can say you have a 95% confident interval, then you have statistical significance. And that means that nothing happens by chance whenever you've got that going on. Okay. All right. Let me see what I want to do. Okay, I'm going to show you how to write this confidence interval real fast. To show the range of values, your interval, you will say this. Okay. Whatever the x bar minus the e is, that's on the bottom side, right? Remember, we're here. And we're saying our mu is somewhere in this area, in that distance. That guy is less than my mu, right? And you could put it in parentheses if you want to. I don't normally. But the mu is less than the x bar plus the error. Okay? So what does that mean? Okay, here's my confidence interval. My mu is somewhere inside of that. So you'll find a number. Maybe this is, I don't know, 22 and this is 45. So there will be values that are on both sides of my mu. So I know that the average for the population is somewhere between these two values. So what we do is we sandwich it, right? We make an inequality. Oh, that pen is dying on me. I need to just throw it away. Make an inequality with the mu, which again, remember that's the population mean inside the two values. All right, so that's what we want to be able to, that's how we want to be able to show our confidence interval, to write it, okay? All right. All of that sounds pretty good to me. I've got a couple of examples of this, and I'm going to go ahead and give you a couple of variables just so that we can go ahead and see them, and then we're going to work with that particular error formula so that we can talk about that. Okay. All right. I'm sorry. I've got lots of different examples here, and I want to make sure that we can work with it. Okay. I'm looking for a particular page. Yep, I got that. Sorry. I'm thinking. All right. Here we go. We have a problem that says, here's an example. It says, consider the daily protein intake data described above for a sample of N equals 267 men. I'm just going to write down what I think is important here. 267 men, and they have a sample mean of X bar equals 77 grams of protein that they ate per day. Okay, so we're talking to men and figuring out exactly how much protein they eat every day. Okay, sample standard deviation of S equals 58.6 grams. Okay, so this is my average. But this is a pretty big standard deviation, right? Okay, so it's going to give me some pretty big numbers. And it says, find the margin of error for a 95% confidence interval. Find the margin of error at 95% confidence interval. And then construct that confidence interval. How does this interval compare to the recommended daily protein intake for men from 55 to 60 grams? Okay, so here's what we need to do. We need to find the error. Okay, so that's the first thing it says. Find the margin of error, and then it said construct the confidence interval. Okay, So first, though, is find the margin of error. Now, this is where that lovely formula that I showed you just a minute ago is going to come into handy for me. E equals 2s divided by the square root of n. Okay, and again, you'll probably need a calculator. It doesn't have to be a scientist. I'm sorry, it doesn't have to be a graphing calculator, but you're probably going to want a calculator to be able to do this stuff. All right, so what we need to be able to do is figure out exactly what my variables are here that I need to plug in. So what's the standard deviation? S. Okay, and in my head, I'm hoping you're saying 58.6. So we got 2 times 58.6. Divide by, and on the bottom I've got a square root, and my n is what? 267. Right, so plug that in, okay? And now just make sure you do things in the right order, right? So I need to do all the multiplying on top, okay, which is 117.2, and I need to take the square root on bottom, so square root 267. 16.34, and then I need to divide. And as much as possible, try to keep this stuff in your calculator, right, so that you don't make crazy little decimal rounding errors too early. So I'm going to try to punch that in as far out as I can. Okay, so this is approximately, now I'm going to round at the end, right, and I'm going to say 7.2. 7.2 grams. So the error in the protein intake is 7.2 grams here, right? Okay. So there's my error. E is approximately equal to 7.2. So that's the first step. Okay. Then I need to construct the confidence interval. So let's see. I need a number line. I need my X bar, which is what? 77. Hope you're following along. Oh, sorry. 70. I cannot write that. I'm going to put it on bottom. 77. I don't know why I'm having a problem. I'm trying to write 7.7. 77. Okay. And then we need to construct the confidence interval. So that means we need to add the 7.2, which is my error. So that's going to be 77 plus 7.2. So what's that? 77 plus 7.2. 1484.2, I hope. Check my arithmetic. So this number up here is X bar plus the E. And then on the bottom side, the distance is 7.2. So this should be X bar minus E. And doing that, it's 77. I don't want to do this one in my head. 77 minus 7.2, 69.8. Don't think less of me because my arithmetic stinks. Please. All right, so here we go. There's my confidence interval, okay? Now, I'm not done yet until I actually write it out, so let's see what we got. Okay, so what we're saying is that this population of men, if the sample is representative, that the population on average eats somewhere between 69.8 grams and 84.2 grams. Right? That's my confidence interval. This is a 95% confidence interval. Okay. So this error that I've got, this 2s divided by square root of n, this guy, remember, this is for the 95% confidence interval. That's the one we're going to stick with. Sometimes in some statistical studies, they really want you to be a lot more accurate, so they want the 99%. But for our purposes, we're going to be pretty happy if we can get 95% confidence. And we're going to say that we have a statistical significance when we do that. So there you go. All right, so there's my confidence interval. That was step 2 that they asked me to do. And then they had a question at the bottom. So it said, let's see what it says. It says, how does this interval right here compare with the recommended daily protein intake that is given by the state that says that they should eat between 55 and 60 grams of protein per day. So the recommended daily allowance from the government, so to speak, says 55 is less than mu is less than 60. You should eat somewhere between 55 and 60. That's what they recommend. I guess it wouldn't be mu, actually. Let me say intake. Not mu, sorry. I'm getting used to writing those intervals. Okay, so what they're saying is that on average, men should eat somewhere between 55 and 60 grams of protein. But that's not what our sample did, right? It's not what our population looks like. Okay, so our confidence interval is right here. So how can we compare this, our confidence interval, to what's recommended by the FDA or whoever does that stuff? It's higher, isn't it? Even the lowest value for us is higher than the highest value that's recommended. So if I compare this, then what that's telling me is that American men, and this was supposed to be American men in this sample, American men on average take in more protein than what is recommended. And it's not just some of them, it's like all of them, right? Because if this is my confidence interval and that's the smallest point, it's way above the highest point for the RDA. Okay, so that's what we're seeing here, is that our American men here, in this case, are eating way more of this than what they would have been. Okay, so that's what's going on there. Yeah, I just want to make sure that I'm doing okay. I do want to show you a couple of variables, so I'm going to throw that out there. And I don't feel like I need to beat this to death with a ton of examples, but I can, if you want me to, make a separate video where we talk about different examples if we want them. Okay? All right. So, okay. I have a little side note here for myself that says if we take more samples, or if we have larger samples, then we can assume that our sample mean is getting closer to the population mean. So it's a good point to make there. Okay, I want to point out these variables. So we already know n is the sample size. We already know x bar is the sample mean. We already know s is the standard deviation. But we've got this mu for population mean. Okay, so I'm going to say over here is population. Over here is sample, right? So mean again for a sample is x bar, right? Okay. Normally we would say S for standard deviation of the sample. Okay. But guess what? Yeah, they have a different variable for standard deviation for the population. And it is also a Greek letter. So they use the lowercase for sigma. Remember, we use the uppercase sigma for summations. Okay, that large capital E. But they're using the lowercase sigma that kind of looks like a 6 on its side for the population standard deviation. Okay, and again, there is a process for, if we know the standard deviation, then I can do an error on it and figure out, oh, I think my population standard deviation is somewhere in this interval as well. But I'm not going to belabor that particular situation. Okay, So, and there's other stuff I can do. So, like, for instance, and I don't want to get too far into it, but if you can find a z-score on the sample, then you can find a similar score on the population. So, and the whole statistics of it starts to get a little more complicated. So that's why I don't want to get too far into that. But I just wanted you to kind of know, oh, we can do this, and there's a lot involved in there. Okay. All right. So those two variables for the population stuff, so that we know those whenever we see them, and they might come out to play with us. It would be good. 95% of the time, my population mean will be inside of the confidence interval that was created using the sample mean and error. Okay. And just remember, it's nothing we did here. Okay. We didn't do anything wrong necessarily. We didn't necessarily do anything wrong. The error occurs anytime you use a sample instead of doing a census on the population. It just happens because it's not going to be exact, because we're estimating, we're representing, right? It's a representative sample, but it's not going to be exact, and there's nothing, it's not that we did anything wrong necessarily. So I want you to be really aware of that. It's not a bad thing necessarily. Okay, final thing I want you to be able to do. We also mentioned at the beginning of the semester, we worked with some problems that were on sample size, if you remember that. Okay. So this error formula helps us pick our sample size. Oh, wait a minute. And it's kind of embedded inside of the formula, and we might not have even known it. But here's what we can do, because I said, oh, it involves a lot of math. We'll figure it out later. So how do you know if your sample size is big enough? That's what people were asking, right? Okay, if I want to poll the entire United States and I want to take a sample, you know, I don't have to do 15 million people. I probably can run a sample about, if I pick it well enough, of about 5,000 people and be okay. If I want to survey A&M Commerce about their favorite color, I don't need to, how do you know how many? I don't need to use in your sample. I don't need to survey 20,000 people to be able to find the favorite color on A&M campus, A&M Commerce campus. I can probably do, it's probably a fairly small number, like 500 or so, and that will give me this 95% confidence level. So here's what we need to think about. The formula was E equals 2s over the square root of n. Okay, so think about it this way. If I want to figure out exactly how big my n should be, then I need to solve for n here. Solve for n. Okay, so what would I do? Multiply both sides by square root of n. Square root of n over 1. Square root of n over 1. Okay, so that gives me the square root of n times e is equal to, these guys go away, right? So 2s. Okay. And then what? I'm trying to get the n by itself, solve for n. So divide by e on both sides. The square root of n is equal to 2s over e, right? And then last but not least, I want the n out of the square root sign, so how can I get rid of a square root? And in my head, I hear you say, square it, and that's correct. Square both sides, okay? So these two will go away, and n equals 2s over e squared, okay? Or you could go ahead and square inside if you wanted to. 4s squared over e squared. Some people like that form better. It doesn't matter. So think about it. If you want an error that's within, and on these problems again, the error would be given to you. The sample or the standard deviation, the S, would be given to you. If you want an error that's, 5 percentage points, and you know your standard deviation, you can just plug those into the formula, and it will spit you out and tell you, oh, well, your sample size needs to be in, whatever that is. So it's kind of a nice way to use this formula to kind of cheat a little bit and go, oh, this formula tells me I only need 500 people, and I'll be able to estimate a 95% confidence interval for what the favorite color is on the A&M Commerce campus. So that formula is going to come in handy if you end up needing to figure out the sample size for yourself. All right? Okay, so I think that's about it for me for sampling errors, statistical significance, and confidence intervals. Just remember, you need to be able to construct that confidence interval so that it looks like some number. Like the example we just did a minute ago, some number is less than your mu is less than some number. Okay, that's your 95% confidence interval. You need to be able to construct that guy. You need to be able to use E, but on these problems, like I'm not going to make you find standard deviation here, right? You've already done standard deviation on another test. I'm going to give you standard deviation. You're going to plug into the formula. So it becomes a little bit easier to work these out. So yeah, you need to be able to do that. You need to be able to talk to me kind of the conceptual about what does it mean to be statistically significant. What does it mean to have a 95% confidence interval? So remember that those conceptual questions, sometimes those really get students on these exams, so make sure you can do that. You understand the background of what's going on. All right, that's it. If you need anything, let me know. Otherwise, have a great day.